So when I say log base 2 of 10, what does that mean? Log base 2 of 10. Madeline, what's that mean? Oh, somebody's chatting me up already. Pyrea. Nope, that was Ruthie. 2 to the what power equals 10. Right on, Ruth. So log base 2 of 10 means 2 to the what power equals 10. Okay, thank you, Ruth. Let's see, Tiger, what about log base 7 of 50? What's that mean, Tiger?
Seven to the power of what equals 50?
7 to the power of what equals 50. Right on. Thank you, sir. KDBF. What about log base 1/2 of 14? What's that mean, Katie?
1/2 to the what power equals 14.
1/2 to the what power equals 14. Right? That's not 14. Piper. What about log base 20 of 0.1? What's that mean?
20 to what power equals 0.1?
See if I can trick you now. Colby. How about log of 5? What's that mean? Ten to the what power equals 5? I was unable to trick Colby. 10 to the what power equals 5. So Colby, remember that log means log base 10. I'll get the next person for sure, though. Who can I trick? Victoria, the natural log of 13. What does that mean? She'll never get this one. Victoria. Psst, Victoria. There we go. And both of you guys put those in the private chat. It would be a wonderful thing to put in the public chat. E to the what power equals 13. Right on. So remembering that natural log is log base E. Okay. So it's really important that you guys are remembering that logarithms are exponents, that logarithms are questions. I really want you guys to be focusing on that, that when you're asked, working with logarithms, we're asking ourselves that question. Because not what we're doing today, we're building towards this, but where we're headed is that, solving these equations. Okay, so if I say if I say log base 2 of x equals 10, okay, or if I say the natural log of x equals 5, how do we figure out what this is? Okay, we need to solve for x, right? And generally our idea with solving for x is that we want to get x by itself. If I say 1/2 x equals 15, or if I say the square root of x equals 15, or if I say x to the 4th equals 15, right? That idea that I want to get x by itself. So how do I get x by itself? Well, I multiply both sides by 2 to get x by itself. Here, how do I get rid of a square root? How do I unsquare root? Well, I would just square both sides to get rid of that, and so then x would be by itself. How do I get rid of a 4th power? Well, I would just take the 4th root of both sides to get rid of that, so I'd have x by itself. Right? So that idea of how do I get x by itself? There's an operation here. This is multiplying by a fraction, so then instead we multiplied by its reciprocal to get rid of that. Here we square rooting, so we unsquare root by squaring. We unfourth powering by fourth rooting. Right? We're undoing the operation that's happening here. You need to recognize this as an operation. Right? The log base 2 is something we're doing to the x. It's not log base 2 times x. Right? It's not multiplying x. It's doing its own thing. A logarithm is its own thing. But it's happening to the x, just like a square root is happening to the x. And same thing, a natural log of x, right? We say the square root of x. So it's happening to the x. Well, how do we unlog base 2? How do we unnatural log? Okay. Well, we know how to unsquare root, right? How do we unlog base 2? And what I really, really, really want you guys to do is to think about that. And the way to undo it is to know what it's asking you. And so what I would have you guys do is when you say log base 2 of x equals 10, you would get rid of that right side, okay, the equal side. Just put your thumb on top of it, okay? And you go back and you say, what does log base 2 of x mean? Right? What's the question? What does it mean? That means 2 to the something equals x, right? Well, 2 to the what equals x? 2 to the 10 equals x. And again, I go and I cross that off with my thumb, right? Cover it up. And I say, what is this asking me? Natural log of x. What does that mean? It means e to the something is x. E to the what is x? E to the fifth is x. Well, look what happened to x, right? Our goal was to get x by itself, and x is by itself. So how did we solve that equation? How did we undo the logarithm? We undid it by turning it into an exponential equation. We undid it by turning it into an exponential equation. And in the same way, if I want to solve an exponential equation, like 15 to the x equals 300, okay, how do I undo that? Well, what happens to the 15, right? Where did the base come from? The base came from the logarithm. So log base 15 of something equals something. What happened here? Where did the x and 5, what happened with the x and the 5? Notice how they switched places. Same thing over here with the x and the 10, right? They switched sides. The 2 dropped down, and then the 10 came over. The x went over. E dropped down, and the 5 came over, and the x went to the other side. So the 15 drops down, and then these two end up switching spots. So log base 15 of 300 equals x. Right? Well, look what happened to the x. Right? X is by itself now. How could we have done that otherwise? Because it's up there in the exponent. I can't take the xth root of something, but I can instead rewrite it as a logarithm. And I need you guys to be fluid in that. Okay? How do you do this? Both ways. Be able to move between the two forms of the equations efficiently, because that's what we need to be able to do in order to solve these equations. How do we solve logarithmics? We turn them into exponentials. How do we solve exponentials? We turn them into logarithmics. Now, x is by itself. We may not know what this is equal to, but we're going to figure out what that's equal to. Okay, we're going to figure out how to figure out that's equal to. Okay? But it is a number. This is a number. Log base 15 of 300 is a number. It means 15 to some power is 300. We just need to figure out what that power is. We're going to talk about how to do that too. Okay? So how do we do the ones that we weren't able to do before, right? We talked about the ones that were easily findable versus the ones that weren't. And on your test, I asked you guys what's the answer if it's easy to find. Well, now we're going to start finding the ones that weren't easy to find. Okay? But this is where we need to be headed, guys, is that we can do this. Okay? That's what we're going to be up to. That's the main meat of this lesson or this unit is to solve these equations. We've been working on a lot of skills to do that first because it's just a different type of thinking. So, okay? That's not fun. Or is it? All right, so we got kind of an info dump here. Okay. We're going to talk about some properties of logarithms in order for us to be able to advance our logarithmic thinking. Okay. You notice that across the top there's 1, 2, and 3. Then down the side there's 4, 5, 6. All right. These are very closely related to the exponent properties that you guys should be very well aware of from Algebra 1 and Algebra 2. Okay, and we talked about them earlier in the year. Okay. And then these first two, we've already talked about. And I do not like the fact that they don't put their arguments in parentheses. I always like to do that. So log base a of 1 equals 0. Basically, log base anything of 1 equals 0. Why is that? Right? If you read this as a question, why is log base a of 1 equal to 0? Because that means a to the what equals 1. This one means 10 to the what equals 1. This one means e to the what equals 1. What power do we raise anything to get it equal 1? We raise it to the 0 power. So basically what this property is a shortcut, guys. If you see log of 1, no matter what the base is, log of 1, the answer is 0. So it's just a shortcut. You don't have to memorize it, but memorizing it will make your work easier, okay? Because then you don't have to sit and figure it out. You can figure it out, or you can just know that any log of 1 is always 0, okay? But again, it's essentially just a shortcut. So the first property is that if you take a log of 1, you get 0. Second property, this part here, we'll talk about in a second, okay? But looking at this part here, log base b of b equals 1. Why does log base b of b equal 1? Well, what does that mean? Log base b of b. That means b to the what power equals b. Well, b to the first power equals b. Or 10 to the what power equals 10. 10 to the first power equals 10. E to the what power equals e. Well, e to the first power equals e, right? And so what you can say here, right, notice how that the base and the argument match. So if you need to write this down, do. Equals 1. So if the base and the argument match, the answer to the logarithm is 1. Every time. Okay? So this part here is kind of a corollary to that. It means it comes from that. Okay? Log base b of b to the x equals x, or log base 3 of 3 to the 6th equals 6. Basically what that comes from is that you're looking at, again, you go to this and say, what does that mean? That would mean 3 to the what equals 3 to the 6th. Well, 3 to the 6th equals 3 to the 6th, right? So the answer is 6. So that's why it happens, okay? But if you kind of notice something more visual about it, log base 3 of 3 to the 6th is just equal to 6. It's almost like these things here are just canceling. It's not what happens, okay? But it looks like that, right? That log base 3 of 3 cancels and we're left with just 6 equals 6. Or log base b of b cancels and we're left with x equals x. So you can kind of see it that way, okay? Again, it's happening because of what's happening over here, or what I just showed you, okay? So what if I talk about this? So what's the natural log of the square root of e equal to? We should be able to figure that out. So what does it mean? What's the natural log of the square root of e mean? Caleb, what's the natural log of the square root of e mean? You there, Caleb? Okay, so what does the natural log of the square root of e mean? I'm not asking what it's equal to, I'm asking what it means. What did the natural log of, what did the natural log of 13 mean? So natural log of 13 means e to the what is 13. So what's the natural log of the square root of e mean? Maria? Oh, there you go. Hey, Caleb. That'd be a wonderful thing to put in the public chat too. E to the what equals the square root of e. So Rhea, what's a different way of saying the square root of e? Something that's equivalent to the square root of e, but different. It's a different way of saying that. I still want the e there. Yeah, square root of 2.7 would be similar, but no, a different way of saying the square root of e. What if I ask you this, Rhea? E to the what is the square root of e? It's a different way of saying that. E squared is the same thing as the square root of e? Yeah. Okay. It's a different way of saying the square root of e, guys. There you go, Caleb. E to the 1/2. Okay. So the natural log of the square root of e is equal to So you guys do need to know this. Okay? This is definitely something that we've talked about, and it is something you will see again while we're doing this stuff. So that's flittered away. You need to bring it back in. Okay? Square root and 1/2 power are the same thing. You guys won't be doing any weird ones. We did like x to the 5/3, and we rewrote that as the cube root of x to the 5th. We won't be doing anything like that. It's just purely put 1/2 in the square root. Okay, that needs to be right there so you don't forget. Okay. So let's see how we rewrite it, make sense of it. Okay, so we can figure out what the answer is. Number 3, we really won't use much. I'm not a big fan of property 3. I think there's a easier way to deal with this stuff, but I'll just quickly explain to you guys. So it's hard to say b to the log base b of x. It's just so awkward. B to the log base b of x, 2 to the log base 2 of 5, e to the natural log of 3. Again, I think visually you kind of see how the 2 and the log base 2 cancel, or the e and the log base e cancel, or the b and the log base b cancel, and you're left with just the x equals x or 5 equals 5. Like visually, you can kind of see how that's happening, and that's not what's happening mathematically, but you can kind of see how those two pieces kind of cancel each other. Remember, exponents and logarithms are inverses, so it'd almost be like multiplying something by 3 and then dividing by 3 at the same time. We would just get that number back. So it's kind of like we're doing that. We're taking that 5 and we're putting it to, taking that 2 to the 5th power, but we're also log basing log base 2 of the 5. And so the log base 2 and then the 2 base kind of cancel each other. So, but yeah, we really won't use property 3 much. All right. So properties 4, 5, and 6 here, these are based off of power rule or exponent rules. I really think that's the easiest way to remember these. 1 and 2 really are shortcuts, right? Log of 1 is always equal to 0, and then when the base and the argument match, the answer is always 1. So these are kind of shortcuts. If you just memorize these, then it's faster. Again, you can figure it out, or you can just memorize it. When these match, it's always equal to 1. And so these are, again, are based off of exponent rules. So the product rule for exponents says something like x squared times x cubed, right? When we multiply powers. What happens when we multiply powers? How does that work, Maddie?
You add the exponents.
Okay, so I do x to the 2 plus 3, right? Which, yeah, the answer is x to the 5th, but the big deal here is that it says multiply, we turn that into addition of exponents. Right? So it happens the same way with logarithms, because logarithms and exponents are very closely related. So I have log base b of m times n, right? That's what that says, m times n. We can rewrite that as log base b of m, again, I like to put the parentheses here, plus the log base b of n. So we're taking that multiplication and we're rewriting it as addition of more logarithms. This first problem they did is pretty arbitrary. I don't know, there's really no reason why they did it the way they did it. Log base 2 of 32. So they saw 32 as 4 times 8. And so they took that 32 and they broke it apart into log base 2 of 4 plus log base 2 of 8. Why they didn't break it into 2 times 16 or 1 times 32, I have no idea. That's why I'm saying it's arbitrary. Okay? We don't usually see problems like that where it's just a number being broken apart. Okay? What we would usually see would have a variable in it. But what I do want you guys to notice here is how the log base 2 doesn't change. Right? The log base 2 is the same through the whole problem. We start off log base 2, we're going to end up with a bunch of log base 2s. Okay? So in that same way, if I start off with natural log of 3x, I'm going to end up with multiple natural logs when I'm done. And I know that I'm going to end up with 2 natural logs because there are 2 things inside the parentheses. And this one's, I think, is a little bit more natural to see. When you look at 3x, you see the 3 and you see the x. So there's 2 things inside the parentheses, and so they each get their own logarithm. So the natural log of 3 plus the natural log of x. So you could break the natural log of 3x apart to the natural log of 3 and the natural log of x. You just add them together. Because with multiplication, order doesn't matter. Because with addition, order doesn't matter. It doesn't matter if you write it natural log of 3 plus natural log of x, or if you write it natural log of x plus natural log of 3. I would just really suggest that you guys don't change the order. It's just a good rule of thumb to just go in the order that it says. So the natural log of 3 first, and then the natural log of x second. Just follow what it says. It's not mathematically wrong, but you're just going to suit yourself better to not change it. So we're breaking apart multiplication into addition of logarithms. So the logarithm of a product, these are going to be kind of wordy, so just watch your size of your handwriting here. You probably need like 2 lines worth of stuff. The logarithm of a product is the sum of the log of one factor and so I'm going to say log / logs, right, because it could be multiple of the other factors, or other factor or factors. Okay, so but again, the big thing here is that multiplication becomes addition of logs. Okay. These are always tricky. I mean, exponent rules mess with people, so then adding logarithms into it just continues to mess with people. Okay, it's really something you have to practice. Okay, it may not make sense until we get to doing it. The quotient rule for exponents would be something like x to the 7th over x to the 4th. How do we do that? How do we do x to the 7th over x to the 4th? Matt? How do we do x to the 7th over x to the 4th? You there, Matt?
One sec.
Yep.
One sec.
When it said multiply, what did we do?
We added the exponents.
So when it says divide, we're going to
Subtract.
okay. So it'd be x to the 7 minus 4. Again, that's really the point, which would, of course, be x to the third. But again, the idea is here that division becomes subtraction. So log base b or log base whatever of some fraction can be rewritten as the log of the numerator minus the log of the denominator. So with division, order matters, and subtraction, order matters. So order matters here. But again, if you just go in the order that it says, you'll be fine. Okay, so order does matter, but if you just follow what it says, it'll take care of itself. Okay, so if you don't know what log base 3 of 27 divided by 9 is, you can rewrite it as log base 3 of 27 minus log base 3 of 9. And then you should know what log base 3 of 27 is. 3 to the what is 27? Well, that'd be 3. And then log base 3 of 9. 3 to the what is 9? Well, that'd be 2. Well, 3 minus 2 would be 1. This would be equal to 1. Well, that should make sense because 27 divided by 9 is 3. Log base 3 of 3 would be 1. So we can use these properties to evaluate things. And this one's pretty easy numbers, but you can use this. What we're going to be using these for is to evaluate logs that maybe normally we couldn't figure out. Okay. Again, this is one that we should know, but I'll just write it this way. Pretend that we don't. Log base 5 of 1/5. So order matters. And the other thing too, again, is the idea that the log base 5 does not change, right? Log base 3, log base 3, log base 3. The log base 5 does not change. Log base 5 of something minus log base 5 of something. It's always the numerator and then the denominator second. Okay. Well, log base 5 of 1. Property 1 says that anything when it's 1, that means it's equal to 0. So this is equal to 0. And then property 2 says that whenever the base and the argument match, that's equal to 1. So this is 1. So 0 minus 1 is negative 1. So this would be equal to negative 1. Well, we should know that. Log base 5 of 1/5. 5 to the what power is 1/5? Well, 5 to the negative 1 power is 1/5. So this isn't equal to negative 1. This is equal to negative 1. All right, we can see that it works. Okay, so we can use this to evaluate logarithms that maybe we couldn't evaluate previously. Oh, here we did one again that we could have. The logarithm of a quotient is the difference of the log of the numerator and the log of the denominator. Okay. Again, big thing, quotient becomes subtraction. Again, order matters, but just follow what it says and you'll be fine. So there's our quotient rule. I think the power rule is the one that's probably like the strangest looking one out of these three. But where it comes from, again, is the power rule for exponents. So x squared cubed. So what is x squared cubed? Or how does that work? How do we take x squared and then cube it? Wesley, how do we take x squared and then cube it? You there, Wesley? Yeah. Ruth, how do we take x squared and cube it?
Multiply.
Multiply what? Multiply what?
the square and the cube.
Okay, so we have x squared times, right, which is, again, x to the 6th, right? So, again, the big idea here is that the power of a power became multiplication of powers, right? And so what I think more visually, right, for you guys, like with this, so log base 2 of 4 cubed, notice what happens. We get log base, or 3 times log base 2 of 4. Again, I would put this in parentheses. I think for me, what I see here is that that exponent comes to the front, right? So just kind of seeing how the exponent drops to the front and then multiplies, right? We said that in multiplication. It does not matter if it's written like this either. Log base 2 of 4 cubed, like where the 3 is inside the parentheses, can also still drop to the front. And this is generally how I would write it. I would not put the dot there. I think sometimes it's easier for you guys to see it because just reminding yourself that this is 3 times some other number. Because remember, log base 2 of 4 is a number that we're doing something to 4. Right? It's like it says, 3 times the square root of 4. Right? We need to figure out what this is equal to. Then we would multiply it by 3. Okay? So generally, I don't put the dot there though. But it doesn't matter. So what about this one? What would that be equal to? What do you think, Andrew? If we want to apply this property, what would natural log of 10 to the negative x power be equal to?
So would it be 1 times negative x?
Like that? Is that what you meant?
I don't know.
Okay. What happened to the 3? What happened to the 3 up here?
Move to the left.
Okay. What happened to this?
It stayed the same.
Okay. So what's going to happen here?
It's going to stay the same.
Okay. So what's the whole thing though? Put it all together.
Is it going to be e to the power 10?
Did this change?
No.
Is that going to change?
No.
Okay. Where did this go?
To the left.
Where's that going to go?
To the left.
Okay. Say it.
So negative x times n to the 10th.
Not to the 10th. Natural log of 10.
Or natural.
Okay. So negative x times the natural log of 10. Okay. That's all it is. Good work. Okay. Just drops to the front. Nothing else changed, right? So again, like I said, this one I think is probably the weirdest of the bunch. So just kind of pay a little bit more attention to it. Logarithm of an expression to a power is the product of the power and the logarithm. Okay. So we're kind of have 2 tasks here with these properties. We're going to use them to expand, basically do what we were just doing. Okay, take like a single logarithm and rewrite it as some sum or difference of multiple logarithms, say simpler logarithms, smaller logarithms, and then we're going to take on the flip side of that is going to be to condense. Okay. which is to take multiple logarithms and push them back together. Okay, so when we're condensing, we mainly use this for evaluating complex logarithms. So if I wanted to figure out what this was equal to, log base 2 of 6x cubed y, if I wanted to figure out what that was equal to, like if those weren't variables, right? If I said, hey, x is 5 and y is 7, what's this equal to? Okay, so if I wanted to evaluate, okay, the condensing is when we want something we'll use to help us solve. Okay, so they have different purposes. We want to pull it apart to help us figure out what it's equal to, and then we want to push it back together to help us figure out what one of the variables inside of the logarithm is equal to. Okay, so so log base 2. So remember with that stuff, right? Log base 3 of this, the log base 3 didn't change, right? We just broke it apart into multiple logs. So as I look at this first thing, I want to just notice that log base 2. I'm going to end up with some series of log base 2s. Okay, and I actually know how many log base 2s I'm going to have. I know that I'm going to have 3 of them. So you should be asking, what should be your question right now? That would be the next question, Maddie. The question you should be asking is, how did I know there was going to be 3 of them? Okay, so I know there's going to be 3 of them because there are 3 things inside of the parentheses. There's a 6, there's an x, and there's a y. And each one of them is going to get their own log. So I have a log base 2 of a 6, log base 2 of x cubed, and log base 2 of y. They each get their own log. Break them all apart. Okay. Then, we want to go down to adding and subtracting. And so what we should notice here is that these are all multiplying. Which means that they are going to all add. That makes sense. 6 times x cubed times y. So that's log base 2 of 6 plus log base 2 of x cubed plus log base 2 of y. So all the multiplication got turned into addition of a separate log. I kind of run this in 2 steps when I do these types of problems. First thing I do is apply number 4 and or number 5. So the product property or the quotient property. So I look to see how I can pull it apart and whether I need addition or subtraction. And then after that, I may have more to do. I look to see number 1, number 2, or number 6, if there's anything to do with there. Again, we won't really use number 3, okay, for the stuff that we're up to. Is everybody cool with how I use property 4 to pull that apart? Does it make sense, Ruthie? Make sense, Matt? Make sense, Tiger? Okay, so I want to look at 1, 2, and 6. Let's look at 1 and 2. Property 1 says that if it's log of 1, then it's equal to 0. Do I have any log of 1s? Log base 2 of 6? Nope. Log base 2 of x? Log base 2 of y? Nope. So no property 1. Property 2 says that if the base and the argument match, it's equal to 1. Well, I have log base 2 of 6. That doesn't match. Log base 2 of x. Nope. Log base 2 of y. Nope. So the argument and the base did not match. So property 2 doesn't matter. Property 6 says that if there's a power, I need to bring it to the front. Any powers? Nope. Power. Oh, there's power. So property 6. So the log base 2 of 6 is not going to change. Plus is not going to change. What's going to happen here? At 3, it's going to drop into the front. So I have 3 times log base 2 of x. Or again, I wouldn't generally write the dot there. I would just write 3 log base 2 of x, just knowing that means multiplication. Okay, but if you need to write the dot because it makes more sense to you, then write the dot. And then log base 2 of y, there's no power there, so that would not change. So there's my expanded logarithm. So each one of these got its own logarithm. That power dropped in front of the x logarithm because it's only on the x, right? It's not on the 6, so there shouldn't be a 3 here. It's only on the x, so it's with the x. And they're all log base 2, okay? So I want to look at this logarithm. I want to see how I can apply property 4 or 5, the product or the quotient rules. First thing I want to do, though, is just identify what the logarithm is. This one's just a natural log. So I'm going to have some series of natural logs. But how many am I going to have? That comes down to is how many things are in the parentheses. So here I have a C, I have an A, and I have a B. So I have a log base, or a natural log of the square root of C. I'm going to have a natural log of A. And I'm going to have a natural log of B. So they all got pulled apart. Okay. Now I go and say, well, what's happening between them? Well, then I go back and I say, well, what's happening inside the parentheses over here? And so what I would notice is that both of these are dividing, right? They're both dividing the C. So that means they're both subtracting. Okay. So quick rule of thumb, anything that's in the denominator should have a minus sign in front of it. Okay. So there's step 1. I've applied 4 or 5 where I could. And I go back and I look for 1, 2, or 6. Property 1 said if there was a 1 inside of there, it's equal to 0. That's not a 1, that's not a 1, that's not a 1. Property 2 says that if the base and the argument are the same, that's log base e, there's no e there. Log base e, there's no e there. Log base e, there's no e there. So property 2 doesn't matter. Property 6 says that if there's an exponent, I need to deal with that. Square root of c is equal to c to the 1/2, which means that this is equal to 1/2 natural log of c minus natural log of a minus the natural log. There's property number 6 again. So seeing those square roots as half powers. Okay. Just I'll let you guys know that the assignment is kind of long, but it, and I know it was me doing it, but as I was doing the homework last night, and it took me less than 5 minutes to do it. Okay. One thing that I did that saved me time was that, when you go to do a log base whatever, in WebAssign, you have to go in and click that button over on the right side. And so instead of clicking the button and then putting the 2 and the 6 there and hitting plus and then a 3, then clicking the button again, hitting the 2 and an X there, and then clicking the plus, and then clicking the button, okay? What I did was I did this one, and I copied it, and I hit +3, pasted it, and then I went and changed the 6 to an X. Plus, pasted it, changed the 6 to a Y. There's a lot less button mashing, and keyboard shortcuts are faster than going and using your mouse and clicking, okay? So I would really suggest that you do that when you have to do a bunch of log-base whatevers. Do it once, copy it, and then just paste it. After that, you're going to save yourself time. Even the next time when I had a completely different problem, like it was log-base 8 of 6, I pasted it and I went and changed the 2. It was still faster to just go and edit the thing rather than have to go and find the button and click it. So I would just tell you guys to do that instead. Let's do one more of these real quick. So log base 7 of 7x over 2. Okay. So again, the first thing I want to notice is what the log is. So log base 7. So I'm going to have a bunch of those. So log base 7. And again, how many am I going to have? There's 1, 2, 3 things inside the parentheses. So I'm going to have 3 log base 7s. Seven and the x are multiplying. That's going to be add. Okay. The 2 is dividing. Become subtract. Okay. So there I applied both 4 and 5 in the same problem. Okay, because the 7 and the x, those are both in the numerator. So it's got added. Everything that was in the denominator, the 2, got subtracted. And then I go looking for 1, 2, or 6. I have no exponents, so number 6 is not going to play here today. None of these are 1, so number 1 won't play. But number 2 says that if these match, this is equal to 1. So there would be my expanded logarithm. So log base 7 of 7x over 2 equals 1 plus log base 7 of x minus log base 7 of 2, our expanded logarithm. So we got through all the slow stuff because we got through all the info dump. So tomorrow, go through and we'll finish this page real fast. It should be pretty quick. This 5 and example 5 is just what we did just backwards, and then the last part's really simple, so it shouldn't take us very long. I definitely recommend you guys get started on the homework. You should be able to do a good chunk of it already, and then you'll be ready to ask questions on anything tomorrow. Okay, but it should go pretty fast.